Okay, it's Friday. It's the first day of spring. It's snowing. What are you going to do? Don't forget the online stuff that you have to have done by this evening, right? There's a deadline today. There was a deadline yesterday, so make sure you keep up with those. We're a ways, it'll be a while before we can do a quiz and a homework for 20, so don't be in a rush to do that. Again, in recitation, we've been going over 19 a little bit. We've been transitioning into 20, and we've been trying to sort of categorize things and put things into little compartments so that you don't have to learn everything twice. We left off on Wednesday talking about oxygen nucleophiles attacking carbonyls, and this is subtle, but it's important, especially for those of you who need to do biochemistry in the future. We can look at this slide again quickly and talk about ketones versus aldehydes and get some appreciation for their differing reactivities. We can see at the top that the ketone here picks up a molecule of water and becomes a hydrate, as does an aldehyde. And if you mix these systems, if you mix water with acetone, it turns out that very little of the hydrate gets formed. But if you mix formaldehyde with water, pretty much exclusively that becomes the hydrate. That can be a problem in biology because the solvent is water, and that can be a problem if you're taking NMR spectra where maybe the sample is wet. So be aware of what's going on here. Subtle electronic effects, subtle steric effects. And again, we're now talking about equilibria, and we will do an awful lot of that over the next few months. This idea that these arrows mean something. They have to mean something. We did a lot of this in the previous semester when we did acid-base chemistry, but now they'll mean a lot in terms of making decisions. How do I know what's going to come next? How do I know if the process is reversible? So what we did is we talked about the subtle factors. Go learn that. If you're not happy with it, ask as soon as you can, because it will snowball here if you get behind. And we started talking about the possible modes of attack and the possible use of catalysis to speed things up. Now, you've always got to remember that catalysis is sort of multifaceted. It speeds things up by lowering transition state energies. It makes things more reactive, and you must get it back at the end. So if we do a catalytic cycle, we must get the catalyst back at the end, and you will see that's consistent. Those two sets of arrows right there, dealing with either basic conditions or acidic conditions, really set up what's to come here. Most of what we'll do here will be under acidic conditions, but there will be some base as well. So we left off with this slide, I believe, and we started talking about the possible use of something called an acetal. Now, acetals show up in carbohydrates. There will be a slide coming up where a carbohydrate is shown as an acetal. Pretty much all the sort of dietary carbohydrates that you take in are linked by acetals, so we need to understand what their structures are, what their stabilities are. And it turns out that acetals are very good for protecting groups. We can see that this acetal doesn't have any acidic protons, and it doesn't react with nucleophiles. And what you've done is you've gotten rid of the carbonyl temporarily. Now, if we need to build this, this is our goal here, then the simplest way to do it is to take an aldehyde or a ketone, mix it with an alcohol, and you need at least 2 equivalents of this alcohol now to be able to form an acetal. Now, this does not happen unless you put the acid in there. It's too slow to happen. So we'll see the mechanism here is fairly complicated. It contains lots of resonance structures, and it is sort of multi-step, but it is indicative of what's to come. We can see now some possibilities here for what to use. The alcohol, if the alcohol is cheap, let's say it's methanol or ethanol or propanol, you just use an excess of it, and you run the reaction with that as the solvent. That's usually a very quick way to do this. The catalyst itself, you could use sulfuric acid, but the problem then might be compatibility with conditions. Maybe your molecules don't dissolve in water, so maybe we have to use something different. And we'll now say that the sort of organic equivalent of sulfuric acid is this molecule at the bottom left, p-toluene sulfonic acid, or tosyl acid. It's the material that is used to make tosyl chloride. But we can use it as an acid because it has a low pKa, and this material will protonate in the mechanism as required. So those are the conditions. As you're starting to catalog chapter 20, make sure you have an entry on your study sheet or study guide, whatever we call these things, about this reaction. It is very important in various different scenarios. Yes, you can make them for their own purposes, but they are usually used for protecting groups. So you need here excess alcohol, carbonyl of some sort, typically aldehyde or ketone, and you produce an acetal. And again, we have this. Okay, this equilibrium idea is going to be key here, because when we say to get the protecting group off, and when we want the reaction to go backwards, we take the acetal and we mix it with water, and we add some acid, and it goes backwards. It's the exact opposite in the mechanism. Okay, so think about what's going on here. This is the mechanism from the book, and then I'll show you one from my website where you can listen to the actual, little narrative about what's happening. You can see here that the carbonyl gets protonated in the first step. That should be absolutely logical by now because we have an acid, it's a strong acid, and it will protonate something quickly. Now, really all we have here are 2 places to protonate. We could protonate on the alcohol itself, or we could protonate on the carbonyl. Both will happen. You'll be able to protonate both, okay? But the productive step is when you protonate on the carbonyl. That allows the carbonyl to become more reactive, because this species here now, the protonated carbonyl, we could draw that as a resonance structure in which this OH group, the oxygen gets its electrons back, and we put the positive charge right there. That looks like a carbocation. It is a resonance stabilized carbocation. That's why it's more reactive. That's where the catalysis is starting to show. So this now, if it's a carbocation, we need to attack it with something. We need to give it some electrons. And in this case, we have lots of solvent. If it's the solvent, the alcohol is the solvent. There's just a lot of it there. It's surrounding these molecules, waiting to do something. And so now we can get this attack. And this arrow here could also be used as this. We could also think about this attacking like that. It's exactly the same thing. You produce a new carbon-oxygen bond, and you've gone from an sp2 carbon to an sp3 carbon. However, once you see this step, and there'll be a lot of this coming up, me sort of hinting and pointing at things that I think should be important. We are putting equilibrium arrows in this mechanism. That's the fact. But you have to understand why they're there and try to appreciate the ideas now. We typically protonate OH groups or OR groups for what purpose? To make them a good leaving group, right? So the conjecture here is this thing can go backwards. We're saying now that this reaction can go backwards. Okay? The second arrow in that equilibrium setup is going backwards. Is that feasible? Is that allowed? You have a protonated OR group. Can that behave as a leaving group? Yes, it can, obviously, right? So this material here is set up to collapse. It can break apart and go backwards. It can only go backwards if the carbocation you're going to produce is allowed and it's stabilized. You're not going to get any primary carbocations here. You might get secondary, but you certainly will get resonance stabilized carbocations. So when we're asking this question, can we go backwards, it's reliant upon the fact that, yes, we have a leaving group attached, and also where we go is fine. Where we go is a resonance stabilized carbocation, so that's why it can go backwards. And it's not sort of unachievable in terms of the energy required. Well, we're going forwards, and we're going to start talking about Le Chatelier. We're going to start talking about the idea of adding excess material and having the equilibrium perturbed so it goes in one direction to favor what you want. So here we go for the rest of the mechanism. I don't need that proton in the product, so I'm going to take it off. We're going to take some solvent here, A, and we're going to pick up that proton, and we're going to get to this stage. And at this stage, we are halfway between a ketone and an acetal. So we use the word hemiacetal. It's halfway there. Glucose is a hemiacetal. We'll show you that a little bit. Now, this needs to go further. We find that the actual product is an acetal, so we need to replace the OH group with an OR group. And what we'll do first of all is activate that system again by using acid. Where did the acid come from? Well, I've regenerated it. There's HA. I've got it back. So I can use it again. Even if I only have a small amount, I can still use it because it keeps getting recycled. The hemiacetal now picks up a proton on the OH group. Why not pick it up on the OR group? Yes, it can. Of course it can. That would be going in the opposite direction in that direction. That can happen. That's why it's reversible. If you put this proton on this basic OH group, which has the same base strength as the OR group, but you go on the OH, you then set this up. The OH2 plus piece is then going to break off. We've always seen that as being a good leaving group, so let's break it off. Now, when we see this type of structure, you might see a little bit different when I show you my interpretation from the website. A little bit extra detail showing you why this is possible. But all that's happening here is the lone pair on this oxygen is helping the leaving group break off. You can imagine the transition state for this process where that CO bond is starting to break. The carbon in the middle, the one that's going to become the carbocation, it's becoming a positive charge. It's sensing that. So anything next door that can help that out should speed this process up. Okay? And that lone pair from this OR group is going to do exactly that. Now we get down to this stage, and that looks an awful lot like where we started, except it's not a proton, it's an R group. And those R groups don't come off like protons. You'll see that is consistent. You can't alkylate, dealkylate these types of things, but you can shuttle a proton around quite easily. We get this species now, which again is electrophilic. That thing is a resonance stabilized carbocation. On my interpretation coming up in a minute from the website, I will draw a structure like this to show the fact that this is a resonance stabilized carbocation. That's why it's so reactive. It needs electron density. We have extra alcohol in there. We have an excess of this material. Again, it could be the solvent if it's cheap. And we can think now that that process would happen again. You get a second attack. And that second attack would lead to this, which is simply the conjugate acid of the product. All you need to do now is lose a proton, and away we go, we have a product. Okay, so where does the proton go? It goes to the solvent. And we're about to see an awful lot of reactions in which, again, lead into biochem, lead into bioorganic synthesis, in which proton transfers become very trivial. We have 20 steps in a process. We have 20 steps in a mechanism. And one of them might be a proton transfer, which indeed is 3 steps. Okay, you proton transfer by picking off a proton and delivering it someplace else. It's usually not intramolecular, but we'll abbreviate that, and I'll show you where that comes up in a second. Right, we'll start to abbreviate that. Proton transfers are fast and they're trivial, and we usually just ignore them. We just say they happen without showing all the detail. So what I have here is I would suggest a mechanism that is fairly straightforward if you understand the basics, and you might have to do some memorizing, but I hope by now people are starting to see the logic, starting to see how things happen. You know what the starting material is, you know what the conditions are, you know the fact that you're an acid, so you should have positive intermediates, and you know what the product is. Most of you, especially the A's and B students, should be able to predict these things from now on, I think. So we've now got a mechanism to go from a carbonyl to an acetal. But we also have a problem, because this process is reversible. What is to stop this just going backwards and forwards and backwards and forwards, and every step doing that? We have to have some conditions to be able to explain or be able to manipulate this system so that it gives us what we want. If you just let this go as it is, you'll probably end up with a mixture of carbonyl right there and a mixture of acetal down there and a whole bunch of protonated things. It would get messy. So Le Chatelier's principle, right? The idea of an equilibrium being perturbed. How can you force an equilibrium to go in the direction you want? Have we ever had to deal with that type of idea? Yes? Distill away the product. Okay? So if you take out a component from one side of the equilibrium will shift to compensate. That's basically Le Chatelier's principle. So if you take out, let's say you were fortunate enough that this acetal was very low boiling, you could distill it away. But the problem in this particular example is that acetone, if you look at acetone, it boils. It's a very, very low boiling liquid. So that's not going to work in this situation. It's a good idea, and if you get the right conditions, it will work, but it's not going to work here. Any other ideas? What's the overall byproduct of going from the ketone at the start, at this beginning here, to the acetal? What's left over that isn't necessarily shown on that picture? Water, right? H2O. Now, any ideas about getting rid of water? How do you get water out of solutions? How do you get water out of mixtures? Say again? A drying agent, absolutely. And you can do that. You can do that, especially in some of the carbohydrate chemistry that we do. You will add a magnesium sulfate to the reaction. Not after you've worked it up. You usually add magnesium sulfate at the end of an extraction to dry up any moisture that's left over. Then you filter and evaporate and you get your product out. Well, we can actually put the magnesium sulfate into the reaction mixture. It's anhydrous. It's been heated high, so the water of crystallization has been forced off, and it wants that water back. So if you put this powder in the mixture, and you're very careful about how you stir the stuff, you can't use one of those spin bars, those small spin bars. You have to use a mechanical stirrer to be able to do this. But the magnesium sulfate will be ready as soon as moisture is formed. It will absorb it, and it will sequester it and take it out of the mixture. So therefore, you can force the equilibrium by removing the water. There are other techniques to do this. You can do what's called an azeotropic distillation, in which water and maybe benzene is used to distill this stuff off. But again, yes, you just need some technique to be able to force the equilibrium. Now, we've done this in several different ways. We've added an excess of the alcohol. That is going to affect the equilibrium because we're going to go in the forward direction more often than the reverse direction. But we can also do something sort of mechanical, like adding a drying agent. So you can do this quite easily, and you can end up with 100% of the acetal. So it's a very, very, very useful reaction. Now, I've got this interpretation from my website, just to give you another example and to put a bit more detail in. The textbook doesn't have some of the resonance structures that I'm concerned about, so I want to show you this as well. I'll show you a slide in a second that says ketones aren't very good at this. Ketones tend to favor the ketone because of the fact that the alkyl groups stabilize the ketone. That's very similar to the hydrate idea. But you can force these reactions to work by setting them up appropriately, by adding an excess of the solvent, by maybe distilling something away or removing one of the products from the right-hand side. So in this example, I have an excess of methanol. That's an easy one because that's a very cheap material. And it's a decent solvent, so maybe these things will dissolve up. I have a catalytic acid. This H plus down here is probably the tosyl acid that we showed on the previous slide. And if you set this up and you do it appropriately, you will get that dimethyl acetal. That dimethyl acetal of cyclohexanone is then a protected form of cyclohexanone. And something you ought to be aware of is the fact that this carbon here has not changed its oxidation state. On the left, it's bonded twice to O. On the right, it's bonded twice to O. It has not changed its oxidation state. It's still the same oxidation state, and that's key. So we'll see in a minute when we take the acetal off and we go back over here that the whole idea of the reversibility of this system is important to be able to go back to the unblocked system. So here we go. We protonate. We have a catalytic amount of acid. People will say, well, why not protonate this stuff? And the answer will be yes, you can. But that doesn't really get you anywhere in terms of forming the product. The fact is we get this product, we need to interpret how we got there. So if we protonate this thing, here's what the book is missing, right? These pictures here I think are key and help you understand why this process is viable. We can see the protonated picture here that the book will put on the previous slide. But if you draw the second resonance structure in which the oxygen is trying to get that lone pair back, don't forget the oxygen had to get protonated because you had a powerful acid. But that oxygen is not happy with giving away a lone pair. It wants it back. So the resonance structure on the right-hand side is to show that. This is now a resonance stabilized carbocation. Dominic. On this one over here, there should be a second lone pair. Yeah, that's fine. Okay. Now you've got the possibility of a carbocation. And carbocations need electrons. This is obviously a better carbocation than we've seen before. And if you go back to the benzene chemistry and look at anisole and look at phenol and why they were so activating and why they were so nucleophilic, here's the same idea. The oxygen gets involved and helps stabilize things. So the next step after this is for this carbocation to attach to something to get rid of the positive charge. And so what we'll do here is go after it with a molecule of the solvent. And for your purposes studying this stuff, all we'll change is the nature of that group, the R group, and we'll change the nature of the aldehyde of the ketone. It's the same thing again and again. With that in mind, I'm drawing resonance structures here because, I'm drawing equilibrium arrows here because in the first step, that's an acid-base reaction. That proton can come off quite easily. That should be okay. Down at the bottom here, this is reversible simply because you have seen this process in the reverse direction before. Where have you seen OR plus break off, giving a carbocation? What reaction does that remind you of? From last semester. E1, right, good, E1. Another one, any others? SN1, right? That was the great determining step in those types of processes. If it was okay back then, it should be okay now. So we have the possibility of going backwards. But now we can see what I'm trying to get at with this proton transfer. And this initially will be confusing because we've been pedantic about this with lone pairs missing and drawing every single resonance structure, and you get points taken off if you don't draw these things. Now we have to be sort of compromise a little bit because the mechanisms are about to get so expansive and so large that you just don't have time to show the proton transfer. And all that's happening is that something is coming along and taking off this proton. What is that something? The solvent. So a solvent molecule comes and gets that proton, and it breaks off as maybe CH3OH2+. And that will give you the neutral species where this thing doesn't have any charge. But then to transfer the proton to the OH group, maybe that protonated solvent molecule comes by the neutral molecule and delivers this proton to this molecule. So all I'll say about this is that it's probably most likely an intermolecular process of shuttling this proton along from one place to the next. It probably is not intramolecular. Well, what you get at the end of this is a protonated version where you have a water molecule as a leaving group. And we've seen this again and again. Water is very capable of breaking off. So let's do exactly that. If we take off that water molecule, this will only happen if the carbocation you're about to produce is okay. And in this example, of course, it's okay again. And yes, I've missed my lone pairs, so I need those in there to be able to show how this works. I have a heteroatom, a non-carbon atom that has lone pairs. Those lone pairs, one of them can be used to help stabilize. So again, I draw my two resonance structures. This is not in the textbook, I don't think, in that scheme that I just showed you. This one is. I want both because I think it helps you understand what's going on. Again, this is happening iteratively. It's happening the same sort of sequence, the same thing again and again. We can see here a carbocation in need of some electron density. We have a lot of solvent. Don't forget the word up here. You have lots of this, plenty of available to behave as a base or to behave as a nucleophile. And if it behaves as a nucleophile, the second equivalent comes in, and we trap this thing. We should then have the acetal product with one proton over, one extra proton. The extra proton being this guy on the methanol molecule. So what comes next is exactly that. And after we lose that proton, we're done. Now, point of sort of order here. Where does that proton go? Well, when we write the mechanisms out, we need to get it back because it's catalytic. If we don't get it back, it's not a catalyst. And we do get it back in that last step. It breaks off. Where does it go? Well, a solvent molecule comes along and it grabs it. And that's all that's happening. But that's a proton transfer. So that's trivial. We're not going to necessarily spend a lot of time on drawing those arrows. What we do need to be concerned about is in the lab, where does that proton go? At the end of the day, when this reaction's finished and you're happy that your material is all product, what would you do to this reaction mixture? What's the first thing you would do? You have an acidic environment and you want to get a neutral product out. What would you add? A base. And you do that an awful lot in the lab, right? You add, if you had the Grignard reagent, you probably had an acid to work up. If you had something negative, you had if you have something positive, you had a base. So in this case, you would add a little bit of base in the separatory funnel, maybe sodium bicarbonate, shake it up a little bit, let the layers separate, and the acid has been neutralized. Now, we can't show that. I can't draw pictures of separatory funnels on my exams, right? I can, but it's just silly. So all of that is that step right there. That's the neutralization step, if you like. You get the proton back and go cycle, but at the end of the day, when you finish with the reaction, we take the proton out by neutralizing it. Simple as that. So we now have what I would argue is a fairly complicated mechanism. It's no more complicated than anything we saw last semester. But what's about to happen is all of these things will come together and they will start to look alike. When we start talking about imines and enamines on Monday, they will look alike, and your job is to keep it all square, keep it all separate. Everybody okay? Kyle. No, because that's killing the equilibrium, isn't it? If you neutralize the catalyst before the reaction's finished, there's no catalyst to speed the reaction up for the rest of the material that hasn't reacted yet. And to summarize that, I always say this as often as I can. Not every molecule reacts at the same time. That's why you have to wait for an hour for things to boil in the lab. You see? So if you did that, you'd kill it. It wouldn't be any good. So just keep an eye on that. Right? You've got various resources to be able to see this and be able to conquer it. Alyssa. You can stop at hemiacetal. There's an example coming up in a second. Carbohydrates in their sort of monomeric form, just glucose itself, is a hemiacetal. You polymerize it to make starch or cellulose, it's an acetal. I'll point that out as we go. But you typically run these reactions to get the product to efficiently, so you use an excess. Okay, so here are some facts. This type of system, again, relies upon the different reactivities of the starter materials. At the top we have an aldehyde, at the bottom we have a ketone. And the fact is, if you simply mix this with two equivalents of the alcohol and you form the acetal, for the aldehyde, the acetal is completely favored. In other words, it goes over here. Maybe I shouldn't say completely favored, but it is favored to this right-hand side. Same argument from the past. Okay? The aldehyde isn't particularly stable, is it? We don't have any alkyl groups stabilizing the carbonyl. And in this case, we have small hydrogens which don't get in each other's way. So there's no steric problem on the right-hand side. So that should mesh and make sense and be the same sort of consistency as the previous example with the hydrates. Now at the bottom, we have a ketone. Ketone is stabilized by electron donation from the alkyl groups. So it's not as reactive. So maybe that favors the left-hand side. And when we get to the right-hand side, we start to get this type of problem. We start to get all these large groups starting to hit each other, and that can destabilize the right-hand side. So it adds up. At equilibrium, that's favored. At equilibrium, that's favored. Now that begs the question, how do you make this reaction work? If for a ketone, the left-hand side is favored, how do you make it work? Well, you play with Le Chatelier's principle. You take out one of the products. Okay? You add an excess of one of the starting materials on the left, and you take out one of the products, and that will drag the equilibrium all the way to the right-hand side. So having said that, this is a really useful way of making these acetals as protecting groups. And this slide, people don't like this slide, but it's no more difficult than what we just did. We have a very useful protecting group. Okay? This thing over here, this cycle, is everywhere. People use this a lot. It's pretty straightforward because you have both alcohols in the same molecule. Instead of using something like methanol, we use this stuff. Any ideas what this stuff is? Antifreeze, right? Ethylene glycol is antifreeze. So it's cheap. It's easy to use. And if you were to add some acid to make this work, it would go through the hemiacetal, which looks like that. But now, if you follow the mechanism through, we will do this in restation. The next step involves protonating this species and making H2O+. And if H2O+ breaks off to give you a carbocation, you have this hydroxyl group right there, waiting to do something. You don't have a bimolecular process which is quite slow where the nucleophile has to find the electrophile. The nucleophile is already there. It's already tied into the molecule. So if this happens and this thing breaks off, this will jump in and start to form a cycle, and ultimately you get a cyclic acetal. And we use this a lot as a protecting group. And this is the chance I'll take to actually say that these things are base stable. These products do not react with bases, okay? But they do react with acid. Okay? So if you add acid to this stuff, it will go back. If you add acid and water, it will go back to the carbonyl starter material. If you add a base, or more usefully, a nucleophile, these things are rocks. They will not break down. So that's really important, because if you bring a nucleophile into this thing, that nucleophile is going to go for that carbonyl. We've seen that a bunch already from chapter 13. If you want to avoid that, you want to get the ketone out of the game for a while, turn it into the acetal. It's not going to look at the nucleophile. There's no delta positive carbon anymore. There's no carbonyl carbon. This does not react with bases or nucleophiles. So put it in as an acetal, and then later on, when you're finished, go backwards. Now, I don't know if there's actually a mechanism for the hydration. I don't think there is a mechanism for the hydration on the slides, but this is something that you should be thinking about how to do now. Going backwards, once you've done your chemistry, maybe there's something over here that's, that's kind of important and expensive, and you needed to be careful how to protect it, and you've done your chemistry. And you want to get rid of this, and you want it to go back to the carbonyl. We just said it's the exact opposite of the acetal formation. It is. You add acid, and you add extra water. Okay, so now you're sort of swamping the mixture with water so that the reverse processes will happen favorably. Well, on the left-hand side now, maybe we can think about Le Chatelier's principle again. We can think about the fact that maybe the ketone is lower boiling. If that's the case, then Pierce, you get your distillation kit out, you boil it away. That's how you drag the equilibrium to the side you want. If not, maybe you can get rid of the alcohol as it gets formed. Something like that will allow you to go back to the ketone. But mechanistically, again, there isn't really a mechanism here. What do you think the first step is of this material under these conditions going back to this? Protonation, absolutely. So you should be able to do these now. Protonate that thing. If you protonate oxygen, what's the purpose of doing that? Make it a leaving group. So you'll probably break one of these bonds and form a carbocation. And then you have water in there. That carbocation can react with the water, and you bring in the OH group. And then you protonate the other oxygen on that cycle, and it breaks off. And then you have a ketone. You're done. So I'm not going to draw the mechanism for that. We might do it in recitation, but anybody who's starting to get this stuff, that shouldn't be too difficult. It's Friday, people. 2 days to study. Okay, so we use them as protecting groups a lot. And here's an example of a multi-step synthesis. We're heading towards that 30, I don't know, is it 35, 37 steps on that problem set? It's a lot. We're heading towards that, and you'll see now that this type of system allows for an awful lot more chemistry than if you don't have this access to this. In this molecule, we have two functional groups. One of them is a ketone, one of them is an ester. I'll tell you, we're not there yet, but the ketone is more reactive than the ester. The ester is stabilized by a lone pair here. The ester is stabilized by electron donation from that lone pair. So if you want to do this job, if that's the product you want, and you can see now we have to introduce 2 hydrogens and get rid of some oxygen. So what type of process is that? That's a reduction. What reagent will allow you to do that? Say again? Zinc and HCl might well work on that, but even more sort of a cheaper, more reliable system that we've seen before. I'm bringing in hydrogen, so what do I need? LAH is the answer, right? LAH. And LAH is a problem because that's a very powerfully nucleophilic source of this, H-. So you have an aldehyde, sorry, you have a ketone and you have an ester. Which do you think reacts first? Ketone, because it's not as stabilized as the ester. So if you're trying to get rid of this, and you want to preserve this, that's not going to work without protecting group. Because it's going to go after the ketone first, you'll get a secondary alcohol, and then sure, it might reduce over here, but that's not what you're after. So what we'll do here is a sequence of reactions in which we get rid of the ketone temporarily. And you could use the methanol here. We're just using this one because it is so useful and it does get a lot of practical use. So we have some acid, and we have the ethylene glycol, and we're removing the water. That's what the minus means. We're taking the water out. And that will give you this blocked. It will form that type of cyclic acetal on this carbon to get rid of the carbonyl. It does not react at the ester. That type of system does not react at the ester. So with that in mind, we then have this out of the game temporarily, and then we can do the reaction where we want to do it, which is at the ester, and then we can quench and we get the product. Now, I want to point this out because it's sometimes a little bit of an issue. To me, that isn't the best way of representing the actual steps that are being taken to finish this off. H3O plus at the end is telling you a whole bunch of different things, and I need to explain this. Don't forget LAH is super basic. H-, right? You end up actually with O-, and then you protonate it. That's what the acid's used for. In the last step of LAH reduction, you need to protonate. But also, it looks like the carbonyl has been revealed. It looks like the material has been deblocked, it's been deprotected. I don't particularly care for that sort of abbreviated way of writing this, because it's really doing two things. That H3O plus is doing two things. And those two things happen at very different rates. So let's think about what's happened here. We've reduced this down, and we still have the acetal, right? So we're still at this stage where the acetal is intact. Now, if you have a negative charge like that on oxygen that's not stabilized, is that basic or not basic? That's quite powerfully basic, right? So what you would do first is add the acid. You'd add a small amount of dilute acid. And what's that doing? Give me a word that describes that. You're adding a small amount of acid to a negative charge. You're quenching it. So I think the first thing that happens is a quench. And that would be a very quick reaction. You might have that in an Erlenmeyer flask, and you add the acid, and then you want to get your product out. Maybe there's something else in the molecule that's acid sensitive, and you want to get the molecule out. So I would argue that this is a two-step process. And this might seem redundant, but when I explain this, hopefully it won't. I would argue, and you'll certainly see this on some of my exams, the first reaction is H3O+, and it might be described as a quench. Quick reaction. Get it neutralized. Then I might do this. Next step, H3O+. Huh? That H3O+ is then put in to hydrolyze the acetal. And hydrolyzing the acetal is a much more complicated process and a longer process than simply quenching. So this here would then be used to hydrolyze. And that's not trivial. You'd have to do it. That's a chemical reaction much more complicated than simply quenching. You see it twice like that, it's not redundant. It's trying to show you that there are two processes, one of which is a quick quench, the second one is an actual chemical reaction to break off the acetal. Jessica 12. I've cancelled all the exams, we're done with exams. No, I want both steps. Yeah. Yeah, H+ will be fine, yeah, that's fine. Rocky. Not at an appreciable rate. If you go back into your notes in 13, which is a long time ago and before spring break for you, it doesn't react fast enough with esters. Right, but technically it's not going to work because esters react too slowly with sodium borohydride. So you need the nuclear option, you need the lithium aluminum hydride to make it work. Yep, so you do need to block. It's a decent idea though. Well played. Everybody all right? Okay. So we now have some useful chemistry here, some things we can use. Well, the question was asked about hemiacetals. We have to define them not so much for this class because they don't really have much utility in terms of their synthetic use, but biology is full of them, and biochemistry is full of them. And again, one of the critiques I get from the biochemists is that students coming from these classes don't have a sound grasp on the functional group. So we need to have to think about that. So what we've got here is the same type of reaction, some ketone, which is exemplified as acetone, simple enough, some excess alcohol, and we have to go through the hemiacetal. No doubt. You go through the hemiacetal to get to the acetal. And the argument is, yes, they are difficult to isolate. Why? Because you have more alcohol, and they trap that alcohol, and they go to the acetal. So now we can think about where that might show up in other places. And I have a couple of slides here to show you why this is useful. If you had a system like this, which is acyclic, and at one end of the molecule you have a functional group, and the other end you have the compatible functional group, you can make that cyclize. Mechanistically, I would hope everybody could have a go at this. What do you think you'll do first? Protonate. I'm going to protonate the carbonyl, and the question will be, why not protonate the alcohol? And the answer will be, you can, but it doesn't get you anywhere. So if you protonate this and you make this into that, you have the same system we just talked about in depth. You have a protonated carbonyl which is reactive as an electrophile, and it wants some electron density. Except now, this has its nucleophile kind of hanging out, waiting to do something, and all you have to do here is cyclize like that. And that gets you a cycle. You lose the proton from this, the extra proton that's left over, you get the proton back as the catalyst, and you're done. You have a hemiacetal. Now, the reason we show you this is because they're not particularly useful synthetically to us, but they do show up in biology. And the best example of that is this, which is glucose. And we will head towards, this is one of the targets now towards the end of the term, is to head towards complex polyfunctional molecules like that, and to be able to have some idea of what they're going to do, and then take it with you to biochem places like that. So this is glucose, and we can write glucose a whole bunch of different ways. You'll get frustrated with this in biochem because we write it many different ways. And it is a very complicated system. We have polyhydroxylated molecule, and at the end you have an aldehyde. Later on we'll draw the Fischer depiction of this, and you'll see why it's useful. And at one end of the material, you have a hydroxyl here, another one there, another one there, there, and there. All with set stereochemistry. We'll understand that later. Now, it seems as if, this has been highlighted. Why not use this? Because why not just do that? Anybody got any comments? Yeah, what size cycle would it be? Seven, wouldn't it? It'd be a 7, right? 7-membered cycles are not as stable as 6. And when we think about glucose as being a way of storing energy, you want it to be a stable molecule. And look at the orientation of all of those hydroxyl groups. What is the common orientation of these hydroxyl groups? Give me a word from the way back when, from the cyclic stuff that we did. The equatorial, absolutely, they're equatorial. So that's a good thing to do, right? You want to put them in equatorial places, which is based on the fact that the nature of the molecule is that. The configuration of each of those carbons sets up the cyclization to give you equatorial material. Well, glucose itself, if you crystallize it, comes out, I think, as the alpha anomer. We'll need to do this a bit later. We'll define what an alpha anomer is later. But it's where the hydroxyl group at carbon 1 is pointing down. That's dextrose. If you buy dextrose or sugar like that, that's what it looks like, crystallized. Now, you mix it into solution, you get a mixture of the two. We'll talk about that in more detail later. But that's the best example of a hemiacetal that you'll see. So why do you need to worry about the mechanisms here? Because most of you are going to be interested in that type of molecule in the future. So we've talked about acetals, and we've got one example here of something called a prodrug. And if you're in pharmacy or medicine or interested in those things, this sort of idea becomes important. These are actually used to deliver drugs. These acetals are used as something called a prodrug. And a prodrug is nothing more complicated than some protected material that then gets metabolized after you take it to produce the free material. Now, why would you want to do that? Well, all sorts of arguments. Maybe this stuff isn't soluble, right, in water. Maybe this stuff isn't stable for very long. And if you just ingest it, it's going to get chewed up and it's not going to make it to where you need it to be. So the acetal here, which is very similar to what we've just done, is going to get removed, and that gives you the active species. Now, where do you find H plus H2O in the body? Where's the most obvious place? Stomach, right? For carbohydrates, your mouth. Salivary amylase will start chewing up acetal linkages in your mouth. And then your stomach, which has a very low pH, and then the gut, and all sorts of other places, in which exactly that is happening. The hydrolysis of an acetal to give a free carbonyl species, or in this case, we don't care about this. This is acetone. Acetone is actually a metabolite, so it doesn't matter that we produce that. And you get this, which has the diol there. And for some reason, I don't know the reason, but for some reason the diol is more stable, and it helps get the material where you need it to be. So with that in mind, I think I'm done with oxygen nucleophiles. I want to spend a second, because I want to set you up for the weekend. Everything we did so far involved oxygen attacking a carbonyl. And we really only did 2 systems. We did hydrates, in which the nucleophile was water. And we did, what else did we do? We did acetals, where the nucleophile is an alcohol. So if you're looking at this chart here, we've done that, and we've done that, and we've done that. From the past, we did that, and we did that, and we did that. So there's a fair amount to do still. But I want to impress upon you that much of what's to happen next, little differences, but a lot of similarities. If you understand the one mechanism, you should be able to have a go at the others. So let's get started on nitrogen, and then we'll hammer this on Monday. We haven't talked a great deal about amines yet. Chapter 23 is all about amines at the end. And then you set up things like amino acids. It turns out that the nomenclature for amines is a little bit complicated. It's a little bit different to alcohols. If I were to draw this, everybody would recognize that as a primary alcohol. Yeah? Because the carbon with the alcohol attached has 1 carbon attached. That was the definition for a primary alcohol. And a secondary would have 2 carbons attached, tertiary would have 3 carbons attached. You've got to be careful with amines because it's slightly different. So an amine is the nitrogen analog of an alcohol. Replace OH with NH2, you have an amine. And we need to worry about things like how reactive they are compared to alcohols. Which do you think is more reactive? Which do you think is more basic? Which is better at giving away a lone pair? Nitrogen or oxygen? Nitrogen, why? Less electronegative, right, it's less electronegative, absolutely. So these things are more basic. Again, we have a lone pair here. They're more basic, but also more nucleophilic. than oxygen nucleophiles. That's a key fact. Now, the definition down here is a primary amine. It's a little bit different, this. A primary amine has one carbon group attached to nitrogen. A secondary amine, and this is where it differs, a secondary amine, like you'll see in the near future, has two carbon groups attached directly at nitrogen. That differs from the alcohol definitions. That's a secondary amine. You put a third group on there, replace the hydrogen with a third group, that's a tertiary amine. They are fundamentally different in terms of their definitions. Well, I'm going to say now that if you take an aldehyde or a ketone and you treat it with an amine, in particular a primary amine, in the presence of an acid, you're going to get something called an imine. And you haven't seen anything about imines yet. This is an absolutely key functional group for biochemistry. This other class I'm teaching, which I'll start to sell towards the end of the term, about biological organic mechanisms for the next spring, imines are everywhere. Okay? Imines are used to temporarily bond things to proteins, do some chemistry, then release, and go back to the carbonyl. So we're about to sort of use these materials to conjugate and to attach things. What you notice now, unlike the alcohols, is that you have this extra valence. If this was a carbonyl, you're stuck with the two valences bonding the oxygen to the carbon. You can't bond anything here pretty much, long term. You can put a proton there, but it'll jump off. If you want to join something else, and this could be, elephants, bananas, whatever else you want, this type of thing over here, this can be expensive, it can be a protein, it can be whatever. That sort of thing is then going to be very, very useful to join things together. So imines are going to have lots of utility. And I want to say before we finish, I've got a couple of minutes left yet, I've never been happy with this mechanism. It makes me grumpy. It's a grumpy mechanism. And the answer to why that is because you look in every different textbook and they'll have a different version of this thing. So we have to be happy, right? It's spring, it's nice out. For some reason, our author of our textbook, in his first edition of this book, which I don't think you have, offers this mechanism as the sequence has shown, where the nucleophilic nitrogen goes after the carbonyl, you produce this O- intermediate, and then you protonate. Now, that doesn't quite fit into our nice, tidy paradigm, because if we have an acid, surely we should protonate something first. And that's why I prefer this version. And I forget exactly which is which. Maybe this is in the new textbook and the other one is in the old. But to cover it and to make it make sense, it's on my website. I prefer this because it fits. I have an acid, let's protonate the carbonyl. Why should I protonate the carbonyl? To make it more reactive. Then the amine comes in, and we get this. And this is starting to look like a hemiacetal. It looks an awful lot like a hemiacetal. If you see that, this mechanism isn't difficult. And then we do a proton transfer, and we get a water molecule that's allowed to break off, and we end up with this species, which is just one proton away from being an imine. So we can see now that this is a condensation reaction. Condensation reactions are reactions in which you visibly see water being produced. You see condensation in the distillation tube if you're doing that. So we're taking out a molecule of water and condensing these two pieces together. And I have, again, conjugated this piece, this R group, onto whatever this is. This isn't very complicated the way we've drawn it there, but you can imagine tying huge things together through this linkage. And of course, we have to keep an eye on this, the fact that it is reversible, the fact that we can go back. So if we form this imine by using an acid, a carbonyl, and maybe an excess of this material, how would you go back? What would you add to the product down here to go back to the starter material? Water. Yeah, if water is the byproduct at the end, then it should be the starter material for the reverse step. But water reacts very slowly with imines, so what should you add instead as well? Acid, an acid catalyst. So again, we'll see that to go backwards here is H plus H2O. But not a simple quench step, not a very fast step that you might do in an Erlenmeyer flask. This is a reaction in its own right. So you should be thinking over the weekend about what's happening there. And I'm going to come back on Monday and look at that again. But examples. It's consistent. You start out with a ketone or an aldehyde, you make the imine if you start with a primary amine. And I want to point out what happens with a secondary amine. You get something very different. A secondary amine gives a different type of functional group called an enamine. Fairly obvious. Alkene, ene, amine, enamine. Enamine, amine. So everybody should know what an enamine is by Monday versus an imine. To get to here, there's a different problem. Why does this give a different outcome? The answer is a secondary amine only has one proton. The byproduct from this process is H2O. I reckon that means I need 2 protons and 1 oxygen. I've got an oxygen here, no problem. I've only got 1 proton from there. But the primary means you had 2. So you could easily get the H2O product by taking off both those protons sequentially. In this case, no. So this one diverts. This one goes someplace else. Instead of just simply condensing, as we did just now, that thing is going to go a little bit different. So I've got a mechanism for that. I'm going to mention this now because I have a couple of minutes, but then do it again on Monday in more detail. Same sort of steps, except again, I don't like this mechanism. I prefer the mechanism where we protonate first, which is probably the thing on my website. This is going to protonate to put H plus right there. This comes in and we start the process off. And on Monday I'll do that in a great amount of detail. So if I were you over the weekend, start thinking about a quiz for next week in recitation, a sit down. Chapter 19, chapter 20, we can tie those things together now, including stuff up through today. If you have any problems this afternoon, come and find me, and then see you on Monday.